Hi, my name is Bianca Bertolino and this is Lab 2 Magnetic Field of a Bar Magnet for Physics 2212. Let's go over the purpose and a review of the main results. We wanted to measure the distance dependence of the magnetic field and compare our observational model to the predictive model and learn about the magnetic field of a dipole and of superposition. A preview of the main results was that B at an angle 45 degrees at a distance d was 3.08 e to the minus 5. There are a few equations that are going to be important for our calculations. So on the left, the two equations are how the magnetic dipole affects the magnitude of the magnetic field, which will be important when we have to calculate mu later on, which is the magnetic dipole moment of our magnet. And then the equation on the right top is for the linearization of our data, and the one on the bottom is an approximation of the magnetic field of a dipole at any given location. Let's quickly discuss the experimental procedure. We set our magnet on one side of the meter stick and place our phone perpendicular to it a few centimeters away from the magnet. We then slid our phone along the meter stick, finding the point where the absolute value of the x component was at a maximum, and then we stuck the tape where the magnetometer sensor was along the line on top of the meter stick. We do the same thing again, but rotate our phone 90 degrees and repeat the steps. Now, continuing with the setup, our system was a magnetometer sensor, our surrounding was a bar and the earth magnet, and the initial conditions were a compensated magnetic north. And now we record the perpendicular distance, which we call d-perp, as seen in the left image, and then we use our magnetometer app to determine the x, y, and z components. Here is the Excel sheet we use for the raw data, and on the right hand side we see the graph of ln(bx) versus ln(r). The next step now is to calculate mu, and we do this by setting our first two equations I showed at the beginning equal to each other. We plug in n, which is the slope of the graph, which was negative 2.76 on my graph, and then we plug in ln k, which was a y-intercept, which was negative 4.047. After we solve this, we get a mu of 3.9665 Newton meters per Tesla. Now let's get to the computational model. We create a function by using our third formula from the beginning, which calculates the magnetic field due to a dipole given a specific dipole moment, and then I needed to set up 6 locations where I visualize the magnetic field. 2 of those locations are on the dipole axis and 4 of them were perpendicular to the axis. In the first picture, our code assigns arrows to those points, and in the next picture we are repeating this process to present the magnetic field 45 degrees from the axis. Here we have our output where the arrows represent the on and off magnetic fields. Our value of 3.08 e to the minus 5 was not quite the same as our predictive model, 5.6 e to the minus 5, but given the assumptions and the errors, we were not that far off. The only 2 statements here that were true were 1 and 4, where the magnetometer is far away from the magnet. It measures close to a zero magnetic field, and as it moved closer to the magnet, the measured x component of the magnetic field increased with it. Our first what-if question is that if we hadn't compensated for the magnetic north and instead put our meter stick at some intermediate angle with respect to the Earth's magnetic field, how would the results have changed? And the answer is that the magnetic field value would have been lower, because it would have been skewed towards the direction of the magnetic north due to the Earth's magnetic field interfering, and there would have been an even larger difference between the experimental value and the predicted model value. The last question is, if we had 2 identical magnets stuck together end to end, how will the measurement differ? And the magnitude will remain the same, but we will assume that the magnetic field will be around twice as large. Thanks for watching.